In this video, we are going to build a logic class using test-driven development. Before we get into that, I wanted to mention a couple of things. So for starters, what is the logic class that we're going to be building? Essentially what we're doing here is we're taking the presentation logic of this application, so presentation meaning to do with the user interface basically, and we're pulling it into this one particular class which has minimal framework and library dependencies. The reason why we're doing that is that if we can write our tests simply with JUnit, is the one framework we'll be using for testing, it's going to mean that we can have an easier time writing our tests. We don't need to learn and maintain a bunch of different testing frameworks. And most importantly, our tests will run really quickly without having to actually deploy to a device. Now, the truth is that although we're putting a bunch of logic in here, there's a couple different kinds of logic in an application, and there's many different ways to actually divide what is fundamentally user interface code, logic code, and model or data code that has to do with data storage and access and things like that. In this particular case, in this application, I've tried to boil things down into like the essence of view binding, logic, and then whatever happens on the back end, which isn't really our concern at the moment. Now, there's a really important point here. So some of you might be new to testing, and you might be wondering which classes are the most important to test. What factor in a class makes it more or less important to test? And that is actually the degree to which it possesses logical complexity. So what is logical complexity? Lots of different things that could happen, lots of different decisions. So for example, instead of having the view, in this case, handle the click events and stuff like that, all we're really doing is we're minimizing what the view does, and we're just passing these events to the logic class so that our view is really simple and therefore doesn't have a high degree of logical complexity. Now, in this style of architecture, the cost of that is that the logic class has a higher degree of logical complexity than some other people might build things. So for example, if you're used to model view model, you probably are aware that there's a bit of an awkward distribution of logic into either the view or the fragment, or maybe 50-50, which can occur. In this case, we are taking extra pains to just make things super separated. So the end result of this is that the view arguably doesn't need to be tested. However, our logic class absolutely needs to be tested, and that's why we'll be building it using test-driven development. Okay, so the first thing we're going to do is, for convenience sake, we're actually going to create the class declaration of our logic class. Now, some people who are kind of TDD purists would say that you're not allowed to write any code until you have a test set up. In this case, my opinion on that is we're not going to be writing any implementation of functions until we have our tests set up and running. But just for convenience sake, I am going to build the class declaration. If you don't know what I'm talking about, don't worry about it. I'm going to right-click on the user interface package and click new Kotlin file or class. And this one is going to be called calculator logic. We're going to say class calculator logic, and we'll just leave the constructor brackets alone for a minute. But this class is going to inherit from our calculator UI.logic class. Now, what we're going to do is we're going to implement the coroutines for this class, and then at the end of the video, I'm going to go back and explain a little bit about how they work. Now, my goal in this video is to show you how to use them. Explaining how they work under the hood isn't really something I can get into in an introductory tutorial, but just understand the way we're going to set this up is going to be, it's only going to require a few steps, and it's going to be very transferable to different things, whether you're talking to a network adapter or a database. It's going to be, this is going to be a blueprint that you can use for doing all kinds of different things. In any case, what we need to do is this class needs to extend coroutine scope. Again, at the moment, don't worry about what that is. We'll worry about the finer details later. Okay, so right off the bat, it's going to be complaining that we need to add some functions in. Before we do that, we're going to add in the classes that our calculator logic will need to deal with. So it is going to need to talk to a view. So we're going to say calculator UI.view, of course. It's going to need to deal with our backend facade, which we'll just call calc, and that will be iCalculator. And then again, this is coroutines implementation. We're going to say val dispatcher, which is a coroutine dispatcher. And again, we'll just talk about that later. So the only other thing I'm going to do before we get started with the test class is I'm just going to click on here, hit Alt-Enter, and then implement as constructor, or sorry, implement members. And make sure you have everything selected. And then we're not actually going to implement these things. Now we'll hop into the test and write the test before we start filling the rest of this information out. Okay, so in the source directory of our module directory, there's going to be a test package. So Android test would be for Espresso tests or user interface tests. In this case, we want just the test directory, which will be where we typically put our unit tests. And that's what we'll be writing today is our unit tests. So we can just go ahead and delete that thing, or actually open up the example unit test class, and we'll just rename it for convenience sake. So our test class is going to be called, I'm just going to hit Shift F6 here, calculator logic test. And that is typically how I name these things. I just write the name of the class that I want to test, and then I write the word test after it. So what I'm going to do for convenience sake and for educational purposes is I'm going to write out at the top of this thing a basic process for test-driven development. So what we're going to do is I'm just going to type, so for number one, create test data and test doubles. I can't type, necessary for the tests. So that's step one that we'll do. Next will be create a copy of the real object we wish to test. Step three, call functions or units on this real object using the test data and test doubles. And I'll explain what a test double is in a minute. And then check the resulting behavior and state. So when we're writing these tests, sometimes we want to know what happens, and sometimes we want to know things about specific data. So for example, if we pass 2 plus 2 into our calculator, does it return 4? However, in this case, we're not going to be testing the implementation of the calculator. We're actually testing primarily the behavior of our calculator logic class. So based on what I've written up here, the first thing we need to do is set up some test data and our test doubles. So we're going to have a couple late init vars. So private late init var view fake. So a fake is, this is a jargon term from testing to denote basically a fake version of a class, which the class we want to test will talk to. The general term is test double, just fake versions of real classes. And here's how we're going to basically make this thing super easy to deal with. So we're going to create a new class called calculator view fake impl. And what we'll do is we'll have this class inherit that particular interface which the logic class will depend on. It will inherit from iCalculator.ui.view, not .ui. And what that's going to do is it's going to make it so that our calculator logic class can talk to this fake version, and it's going to have no idea, nor is it going to care. So what we'll do is within the same test package, I'm going to right click and create this new class. So that's calculator, forgot what I called it, view fake impl. So we're going to type class, and then that, as I said before, it's going to extend our iCalculatorUI.view interface. We'll implement those methods. It's going to be display and show error. And we're going to have a couple different things in here. So, of course, we have our display and we have our show error. But what we're going to do is we're going to want some things in this class which we can kind of control to set up different behavior and scenarios. Mainly, a lot of things we're going to be adding to these fakes are booleans. Is this called? Was that called? So we're going to add a couple things in here. So I'm going to take var set display called as a boolean. And the default values for these things are going to be false, but these are going to be things we can change based on what we want to have happen. So set display called. So was this particular setter called? We'll have get display. So we want to know if get display was called. And we also have show error called. If you've ever used a mocking library, this is very similar to like verification statements. And then we also have just an expression for something that the display will return. By default, it's just going to be an empty string. And what we'll do next is we'll code out our display property here. So for our getter, what we want to type, just make some curly brackets, and we're going to say get display called equals true, so that we know if this thing was called. And then we're going to return expression, and that'll just handle the defaults. We'll remove that equals sign there, and that should fix that. And then for our setter, we're going to call set display called equals true, and then return expression, or wait, no, sorry, reading the wrong thing on the side here. Expression equals value, so whatever was passed into the setter function. And we're also going to do a similar thing with show error. All we're going to do here is we're just going to make sure show error called equals true. And what we're going to do is we're going to be able to basically check these booleans in our test function just to make sure that the things we want to have called are actually being called. Okay, so returning to our test class, we're also going to need to create a calculator fake. So we're going to call this thing calc fake, and this thing is going to be called just calculator fake impl. And we're going to do the same thing as we did with the previous fake class. So I'm going to right click on the test package, go to new Kotlin file or class, calculator fake impl. Class inherits from the same interface by calculator. Implement the members. And so all we need with this particular class is we just need one boolean var succeed. And so what this is going to dictate is if succeed is set to true, then we'll return a basically an expression or a successful situation. If it's set to false, then what we'll do is we'll return an exception. So as I mentioned before, what's going to happen here is we're actually going to be passing in a callback function from our logic class. So this is something a little bit different, but just understand that, as I said before, another thing you could do is you could just like return a result wrapper normally if you wanted to simplify things. I think this will be a little bit interesting for some of the people who aren't used to using function references. So we're going to type if succeed callback.invoke. So invoke is how we invoke a function that's passed in. And we're going to give that a result wrapper .build. And it's just going to be 4 because the test expression will pass in will be 2 plus 2. Then I'll hit Control, I'll hit Control D. That's a little more concise. And we'll type else. Otherwise, we want to throw an exception. So instead of typing that, we're going to type throw exception, like so. And that is all we need to do for this fake. Okay, so we have our 2 fake classes. There's one more dependency we need to satisfy, which is the dispatcher. So for here, we're going to type private val dispatcher. And again, this has to do with the coroutines. Equals dispatchers dot unconfined. So what does this mean? So when we're working with the actual operating system, we want to be returning dispatchers dot main or working with dispatchers.io in the backend. In this particular case, what we want to be doing is using this dispatchers.unconfined is going to allow us to execute our tests without having to mess around with different threads. And the reason we need to do that is because we're not actually working with the Android operating system here. We're just working with simple JUnit tests. So we'll also make a reference to the calculator class. So we'll call this calculator logic of type calculator logic. And then we can get to work writing our test classes. Okay, so now that we have all of that set up, which was step 1, we're going to actually write our test class where we'll need to create a copy of the real object we wish to test. So we're going to rename this test function. Now I'm going to use the backtick character, which is underneath the tilde key, which should be in like the top left of your keyboard roughly beside 1. And these backticks are going to basically allow us to write plain English or plain language names for the different tests we have. So this one's going to be called onEvaluate event success. So the names basically refer to the different view events which we've represented as a sealed class in our interface, and then what we want to actually happen in that particular test case. Now, how I write these tests in production code is I will write the user story or problem statement first, and then either that will be an itemized list, or right after that I'll write an itemized list of the steps that I want to write. This is the actual process I follow. I don't suggest you skip writing these comments. So on evaluate. So what do we want to have happen with our implementation here in just plain language? So 1, get current display state from the view. So we need to know what is inputted in the view. Give the state to calc for evaluation. So of course we need to give it to evaluate. And then verify callback invoked on callback invoked on the view. So what does this basically mean? We want to make sure we're grabbing the state of the view, giving it to the calculator, and then giving it back to the view when evaluation is successful. So what we'll do is we're going to get rid of this assert equals statement here that was automatically added, and we're going to create our fakes for each test case. So view fake equals calculator view fake impl, calc fake equals calculator fake impl, and then we will create our logic class using those fakes. Calculator logic equals calculator logic, and we're going to pass in view fake, calc fake, and our dispatcher. And there you have it, the power of dependency injection and abstraction. Now, the next thing is we want to call the actual unit which we want to test. So that's going to be calculator logic dot handle view event. So the reason why I have this kind of handle view event function here is I want a single entry point for pretty much all of the publicly available functions within the calculator logic class. Now we also have, of course, the handle result function. But the idea here is, generally speaking, I find it to be just a really handy pattern to have some kind of function which inputs some kind of sealed class to represent all these different events. Now, of course, the actual event that we'll be dealing with is view event.evaluate. So we're calling the actual function, and then we need to, as we say up here, check the resulting behavior and state. All right, so one other thing I forgot to do. So we want to make sure that our calculator succeeds. So we need to type calc fake dot succeed equals true in this particular case. And then what we need to do is we're going to be using some JUnit 5 assertion statements to verify our behavior. So we're going to type assert true that view fake dot get display was called, and also that set display is called. Now you might be wondering, why aren't we making sure that the calc fake was called? Well, basically we will know that it will have been called if set display called gets called eventually. So we're basically able to handle both those cases through one assertion statement. So this is all we need to write for this particular test class. Now, returning to a more traditional TDD process, we will run our test function here. Now, it's not going to pass, but what we're trying to do here is we're just trying to make sure that our test is well formed. So we want it to fail because we haven't implemented it, not because we've screwed up writing our test or something like that, or some kind of compilation failure. So I'm going to go ahead and run this and we'll see what happens. Okay, so I am getting compilation failure, which is not what we want to see, and it's calling that based on assertion references to different JUnit functions. So what I'm going to do is I'm just going to look at our import functions, and I see that we do not have the proper version of JUnit imported here. We have the JUnit 4 version. So I'm just going to delete those import statements, and then it should basically add in this is what we want to see. JUnit Jupyter will be JUnit 5. So this should be working properly now. Let's just go ahead. So this is exactly why we execute a test, even though we know it's going to fail, just to see if it's well formed. Okay, and this is what we want to see here. So it's probably really hard to read here, but an operation is not implemented. So this is actually an error which pops up when we reach a to-do statement here, and that's exactly what we want to see. So like I said, with traditional TDD, you're not supposed to write the implementation until you have a failing test. Now, but a failing but well-formed test. That's exactly what we have. So now we can go in and implement our unit until the test is passing properly. Okay, so jumping into calculator logic, we're going to begin by implementing part of our handle view event function here. So I'm always going to have a when statement on the event, and then we will use this as kind of like a filter for the different events which can pop up. So when event is view event.evaluate, which was the one which we are calling, then we're going to call a helper function evaluate expression. And we don't need to pass any data into that function. I'm going to hit Alt-Enter, create function evaluate expression. And so immediately what we need to do is, since the interface for calculator is coroutine based, it has suspend functions, we need to immediately jump into coroutines land, I'll just call it. How we're going to do that is with a launch coroutine builder. Again, for the time being, just type what I'm writing here. Don't worry about the finer details. I will talk about it more later. So we're going to say equals launch, just like so. Now, the actual function that we're going to be implementing here is really easy to write. We're just going to call on our calculator function here, calculator interface, calc.evaluate interface, evaluate expression, view.display. So we're grabbing the display of the view. And now what we need to do is we need to give it a function which accepts a result wrapper of this particular type. Conveniently, we have that right here. So in Kotlin, as we learned before, when you want to create and send a reference to a function, you type :, and then the name of the function. So here we have handle result. Okay, so I know this is going to fail because we haven't implemented handle result, but just for fun, let's go ahead and run that test case again and see what happens. So curiously, it is failing at our coroutine context, so we're going to want to fix that right away. So how we're going to fix this is we are going to supply our dispatcher that was passed in, and then we're going to create a job object. So we're going to type protected val job tracker is what I like to call it, and it's going to be of type job, and this is coroutine stuff again. And then we're going to say dispatcher plus job tracker. I understand this is like completely unintelligible if you're not familiar with coroutines. I've said it 1,000 times, just type it in and we'll talk about it later. So the next thing we're going to do is we're going to run that test again to see where it's failing. Okay, so in this case we're now failing because of an assertion, which is what I wanted to see. So that's all right. Let's carry on and keep implementing the functions until things work properly. So what we'll implement next is the handle result function. So again, we're going to have a when clause here. When result is result wrapper dot success. Then we want to, of course, give that value to the view. So we say view.display equals result.value. I'm going to hit Control D when result wrapper is error. Then what we want to do is we want to say view.show error generic error message, which is of course again from our contract file. And that's all we need to do there. So let's see if our test is passing now. And there we go. Okay, so as you can see, we've implemented the first function in our calculator logic class using test-driven development, and we have a number of other functions to implement. So we need to handle delete, delete all, and the input functions. So I'm not actually going to code those along with you because otherwise this video would be about an hour and a half long and it would be very tedious and repetitive. So basically that comes down to two things. If you would like to practice test-driven development yourself, then I'm going to suggest that you finish off all of the different tests and don't forget to include things like a failure case for our evaluation. And if you're not really into that, then what you want to do instead is you'll want to open up the completed project and just copy and paste the classes or the rest of the test-driven development functions into this file here. And then also make sure you copy and paste the correct implementation of our calculator logic class back into the calculator logic class. What we'll do in the rest of this video is talk a little bit about coroutines. Okay, so I've copied and pasted in the rest of calculator logic and also the rest of the test classes. And I made sure to rerun the test suite to make sure nothing is broken or I didn't copy paste something incorrectly. What we'll talk about now is coroutines. So we have a bit of a dilemma here. I can't really explain to you how coroutines work in a way which is really accurate with how they work under the hood and still make this explanation intelligible to you. Now, the thing about this is that coroutines are actually pretty complicated, and the reason why is that the whole subject of concurrency, multiple things happening at once in a computer, is possibly the most complicated topic in computing in general, if not one of the most complicated. What I can do for you in this video is explain a couple steps you can take to set up coroutines in a particular class and how to use that class as kind of like a launch pad for back-end operations. Now, if this doesn't make a whole lot of sense, I do apologize, but like I said before, it's just not something that's very simple. I will do my best. So the first thing you're going to want to do is you want to pick some particular class in your architecture, which will be the root coroutine scope. Now, some people will just make that an activity. If you're not into building applications in a flexible modular way, then by all means you can certainly make your activity the root coroutine scope. You can make a view model a coroutine scope. That's okay. In this case, we have our logic class as the root coroutine scope. Whatever class you pick, you want to either pick a class which has a life cycle or has some kind of connection to the life cycle so that it can be stopped. So when we added this coroutine scope interface here, notice how this overridden property down here goes red. So when we add in a coroutine scope, it requires us to add in this coroutine context object. So again, it's tough to explain simply, but this coroutine context object is kind of like a map, like a Java map or Kotlin map, and it's able to keep track of coroutines which we launch from this coroutine scope, this object. What does this mean? All we're doing here is this coroutine context by combining it with a dispatcher, which basically tells the coroutine setup what thread we want to run our coroutines on, with this job tracker object, which is just a way of canceling coroutines. When we combine these two things in our coroutine context, the result is that we have asynchronous functions via things like the launch coroutine builder, which can be called as extension functions on this particular object Notice how this launch statement here is showing up as gold. That means it's an extension function of our calculator logic class, and that is possible because it implements coroutine scope. This is going to allow us to launch asynchronous coroutines from this object, and also they can be canceled. We don't actually really need to cancel them in this particular applications, but in many applications you would want to have them cancelable. So that's just a really simplified explanation of the stuff we added in. This thing just makes things cancelable, so we could do something like job tracker.cancel. And just like RxJava, if you've ever worked with it, this is just like calling dispose or clear on a composite disposable. What that allows us to do is if we have some stuff going on in the back end and the user leaves the current feature, we can cancel everything so that we don't get null pointer exceptions from calling back to things that don't exist. Anyways, back to the only other thing here. So we're using that, and then we're also using this launch coroutine builder. We want to use this launch coroutine builder whenever we're calling a suspend function, which happens to be our evaluate expression. Another way of putting this is anytime we want to jump into asynchronous operations so that we're not blocking the main thread, but we're still solving problems, we want to use a launch coroutine builder. You can also use async. I prefer launch, and the reason why is that it allows me to write asynchronous code in direct style, which means I don't have to have callbacks. So probably that sounded pretty complicated and didn't make a whole lot of sense. Again, there's just no easy way for me to explain this, but just understand when you want to use coroutines, mark some object which talks to your backend tools which have long-running operations as a coroutine scope. Add in this job tracker object, or you can call it job, call it whatever you want, and that will make your stuff cancelable. We'll see what actual dispatcher we use when we write our dependency injection implementation. When we're writing tests, we use unconfined, and we use something else when we're using the actual application. And then when we want to call a suspend function, which is a function that can work asynchronously, we call it from a function which is a launch coroutine builder. There are lots of different ways to set up coroutines. You can use channels, actors, async, but as I said before, launch is generally pretty simple. So that's it for this lesson. On my YouTube channel, I do have a couple videos where I go into the internals of coroutines and also kind of give a more detailed explanation of it. But my goal here was just to show you the basic setup. And as you can see, it's not that complicated. You just need to follow a couple steps, but it is very confusing to understand.